And the rest part of my talk, I will tell you about optoplasmonic sensors. Correspondingly, the first part was done at the Ersten Institute and the second part in Exeter. Let's start with considering a light pulse in free space or in an optical fiber as it's shown here. Speed of light is equal to the distance over time, and approximately in 2008 there was a meeting about slowing light, and a special issue of the prestigious journal Nature Photonics was devoted to slow light. The basic idea of slow light is creating photonic circuits where the light propagation is limited via different means. There are three most common ideas for the fabrication of photonic circuits with slow light. First of them is just simply using curved waveguides from the materials with high refractive indexes where the light physically propagates during a longer time than in free space. And the second and the third approaches at the moment are more sophisticated. They supposed the nanoengineering to be used for creating ring resonators, like it's shown here, where the light can be circulating during a long time, or one of the basic technologies as photonic crystals fabrication. In course of slow light, they provide the basis for optical delay lines and buffers, as well as photonic circuits for signal processing, classical and quantum optics. But such kind of technologies has a number of problems with the dispersion of signals, losses, and scattering of light. These problems were formulated, for example, in this work already 13 years ago, and up to date they exist because of more complicated techniques are exploiting the elements consisting of nanostructures, which can be fabricated with impressive values of precision down to 3 nanometers. But nevertheless, this precision is still not enough for the fabrication of devices with a significant delay time of light without its attenuation and dispersion. In our work, we developed the technological platform for creating slow light photonic circuits, overcoming well-known devices by a parameter of attenuation. Namely, we use optical fibers, which are exploiting for telecommunications. And at the surface of optical fibers, we fabricate the structures with a precision better than sub-Angstrom scale, or 2 orders of magnitude in comparison with photonic crystals, or for example, silicon waveguides. The fundamental basement of our technology exploits whispering gallery modes that can be excited in an optical fiber, like shown here, making an inhomogeneity at the fiber surface. We introduce a resonator for whispering gallery modes where these modes completely confined. For this, the nanoscale inhomogeneity is enough, and a whispering gallery mode for with cutoff frequency in an optical range of spectra has a small component of the electric field that is propagating along the fiber. But the propagation constant beta tends to 0. Thus, we can observe the slow light in axial modes circulating mainly in the fiber. Since we have optical fibers with small attenuation at optical wavelengths, the losses are very small. It's less than units of dB per kilometer. The central idea of SNAP, or this platform, is called Surface Nanoscale Axial Photonics. The central idea of this platform is to exploit the sensitivity of whispering gallery modes to the extremely small variations of the fiber radius and refractive indexes near the resonance frequency. In SNAP, a variation of delta R and delta N, depending on Z, is so small and smooth that dependence of the whispering gallery mode field of the axial coordinate psi is defined by a single differential equation here is the field distribution of Whispering Gallery mode propagating along the z-axis of a fiber with nanoscale radius variation. Here, z, rho, phi are the cylindrical coordinates. M is the discrete azimuthal number, or it's called quantum number also. I will show why. Function psi on z and t determines the axial distribution of the Whispering Gallery mode and satisfies the one-dimensional Schrödinger equation near the resonance wavelength, which is presented here. As SNAP devices includes three main building blocks, which are illustrated in this figure. The first part is the Whispering Gallery mode microbottle microresonator, which is coupled to a microfiber exciting Whispering Gallery mode inside the resonator. This corresponds to a quantum well with the potential V on Z and leads to the formation of states localized between turning points ZT1 and ZT2 at a discrete series of wavelengths corresponding to resonances in the transmission amplitude. Resonance transmission amplitude is proportional to the Whispering Gallery mode amplitude at the microfiber position Z1. A second building block is a concave fiber waist. In this case, for wavelengths in the under-barrier region, the Whispering Gallery mode is localized due to the exponential decay of its amplitude away from the microfiber position Z1. Alternatively, above the barrier, the excited Whispering Gallery mode is delocalized. In particular case, for a uniform fiber where delta R is equal to 0, this part offers a simple explanation of the localization of light in a uniform cylindrical microresonator. And the third building block, where the microfiber is positioned near a turning point ZT, where the SNAP device has monotonically increasing radius. In this case, the wave that is launched by the microfiber along the positive axial direction interferes with the wave that is launching along the negative direction and reflects from the turning point ZT at discrete wavelengths when the condition of destructive interference of these two wavelengths is fulfilled. The distribution of light is fully localized between the turning point ZT and the microfiber position Z1. It's like the same in Mach-Zehnder interferometer. To fabricate real SNAP devices, there are a lot of different methods. Actually, I know that many of people who deal with this problem, they know just two methods. So it's a fabrication with CO2 laser annealing and with femtosecond laser. But to my knowledge, there are 8 different techniques for the fabrication of Whispering Gallery mode resonator for SNAP platform. The most well-known technology of fibers, all of these devices, they used fibers, just ordinary standard SMF28 fiber, or maybe capillary fiber. And the most well-known technology of fiber fabrication in general is they're drawing from melted silicon. The frozen in tension is introduced by the pulling force in the process of fiber drawing. Using CO2 laser, in first case, focused beam of the CO2 laser, we can decrease these tensions and that result in the refractive index and physical radius changes. The second technique is the fabrication with femtosecond laser inscription. Actually, the laser beam here was focused into the middle of the optical fiber, and it creates bursts inside the fiber and introduces additional tenses from the inside, which is smoothly changes effective radius of the optical fiber. One more technique is a mechanical bending. It's based on elasto-optic effect. And actually, I'm going to tell you about each of these techniques. but except this one, slow cooking, it was published when I already left Aston, and it's a very interesting technique, and at the same time very complicated because it involves a lot of chemistry. It's because when you have a capillary fiber and when you have a water droplet inside, and you start to measure your spectra during the heating process, during the measuring, and if you do it a very long time, like 20 hours or even more, the water starts to react, chemically react with the quartz, with the capillary walls of capillary. And after several tens of hours, you can achieve smooth changes and very, very tiny changes of effective radius. So, CO2 laser inscription of snubs. Here is a nice sketch of this process which illustrates everything. You have optical fiber, you have CO2 pulses. It's about millisecond pulses. It depends on the chopper you used for CO2 laser, because laser itself is a continuous wave. You introduce these homogeneities, and after that you can characterize it just touching the microfiber, which is connected to optical spectrum analyzer. We used to work with Luna, and depending, it's a very nice picture of Sumetsky. He drew it many years ago, I guess. And touching the fiber, you can measure the spectrum of Western gallery mode, and when you observe a wavelength shift of Western gallery mode, it corresponds to changes of effective radius, and it can be recalculated to using this ray-scaling relation. It should be noted that changes of effective radius are really tiny. It's about 3 nanometers here. And the natural question is, what's the limit of precision? Because 3 nanometers, it's comparable to silicon photonics, for example. And to demonstrate what's the precision, you have a question?
Yes, Nikita. So could you switch to the previous slide, please? So I would like, let's have a look at this beautiful figure. But we see that upper region above the blue line, I mean this here, and below this WGM, we have like a different figure, different character of the plot. So could you comment on it, please? So below and above this.
Oh, you mean green and yellow?
Yes, then it's like qualitatively they're different for some reason, but I didn't get why.
No, I would say they are not different. It's just a background. Actually, what you need to see is a blue line. Blue line, it's a resonance. The rest part is just a background. I don't think it's really meaningful.
Yes, you have, because it's a transmission, amplitude. Yeah. And exactly at WGM, you have like a zero transmission. Yeah.
No, it's not a zero transmission, but it depends on the depth of your resonance.
Yeah, exactly. Okay, thank you.
So, what is the precision? The question is, what's the precision? For this, we fabricated 2 microresonators very close to each other. We used to work with 20 micron radius optical fiber, which was specially drawn by OFS Labs, I think, in America. We fabricated 2 resonators with CO2 laser annealing. We just corrected them and achieved perfect matching. Here you can see these 2 resonators, and we checked spectra at different points. For example, 1, 2, 3, and 4 points, you can see the stable line. But when you go to points 5, 6, 7, 8, and 9, you can see this splitting. And that I was talking about, it's a quantum analogy, because when in quantum mechanics, you have 2 systems which are close to each other, and they have the similar energy levels. Their level can demonstrate splitting. And this splitting, it seems like we observe it here, and which we checked many times, because maybe the resonance is not stable, because quality factor of optical microresonators is really high, and it is very sensitive to environment. It is very sensitive to the vibrations around. Even if you switch on the air condition, you can see the changes of resonance wavelength, but it did not happen. The system was isolated quite good enough. And this level splitting is a fantastic phenomenon, and I was really excited to observe it. But from fantastic phenomena to application, which is more interesting for funding usually, we should consider now the first and one of the most exciting application to my mind. It's a delay line. I think most of you already saw this picture because Misha gave a talk, but I will tell this story on my own manner. So I would like to present this delay line. The scheme of the delay line is presented here. We send an optical pulse into a tapered fiber using the same optical vector analyzer. The wavelength of tapered fiber is about 1 micron because we need to obtain evanescent field, which evanescent field which will penetrate inside the fiber. And after several moments, after several nanoseconds, the pulse will go back. And the question is, how long can we delay the pulse? And it is quite long. Misha used to fabricate this resonator in 2013, and I think, or I would say to the best of my knowledge, it is still a record precision, still record delay time, and it's still record intrinsic losses, especially in comparison with silicon technology, where insertion losses, intrinsic losses are very high. Here we estimate them like 0.44 dB per nanoseconds of delay. And for this, it just was fabricated 2.8 nanometer height resonator with a parabolic profile. And I was going to mention, record slow light for engineered device. It's C over 250. One problem which should be solved here, if you can see, there is a slope here, and this slope is not good enough for application because you need to select the proper position for tapered fiber where you send your pulse, and it's better to get rid of this slope. And it was actually a nice effort to get rid of it. Here, that's what I'm talking about. You have, for example, changes of effective radius like 1 nanometer, but at the same time, you have a slope about 50 microns, and it's better to make it really sharp. And if you use CO2 laser, the most influential effect is the heating. But that means you need to get rid of this heating and use a different laser. And of course, it's first thing you have in mind, it's a femtosecond laser. And this technology, this technique was proposed to fabricate SNAP resonators. And if you have the beam focused inside the microfiber, and you introduce stresses from inside the fiber, actually, it's a core of the fiber. You can see optical image here. You can obtain quite nice optical microresonators, but slope is not good enough. There was no improvements of the slope. The perfect thing of this technique is you can use now any different material and introduce optical microresonators in chalcogenides or whatever you want. It is not necessary to fabricate optical fibers even. But when you change the experiment and when you focus laser beam, femtosecond laser beam, just at the surface of the fiber, like it presented here, you can obtain achievements 50 times better. That means you have, instead of 50 micron slope, you will have 1 micron slope. And here we present nice try to reduce the dispersion, but it was fabricated. It was measured for rectangular shape resonator fabricated here with a longitudinal size at 2.58 microns. And when you send 200 picosecond pulse, you can see 342 after the system, after it went to the system and went back. So it's because of dispersion of group velocity, and the rectangular shape resonator is not good enough for application in delay lights. It should be like in composition with CO2 laser annealing and femtosecond laser inscription. And Misha explained this phenomenon in 2015 using Schrödinger's equation. Again, it's based on quantum mechanical analogy. If you have a parabolic potential, that means you have no dispersion. But at the same time, when you have rectangular, it's because the group velocity of different modes is different. You will have very huge dispersion. So on this slide also, I'm presenting the concept of reconfigurable optical buffer. The scheme is quite simple. You have a microresonator introduced at the surface of optical fiber. At some point, you can open this optical microresonator and send the pulse. The pulse should go back and forth in this resonator for quite a long time, but of course, long it's just a nanosecond, or if you achieve millisecond, you will be close to the Nobel Prize, I guess. And at some point, resonator should be opened. The main problem is dispersion again, because when the light is bouncing inside, it will accumulate dispersion. And to avoid it, you need to fabricate this device with very nice precision. We tried to fabricate this device because it's a really nice concept, but realization was not such nice. It's because, the scheme of the experiments is quite simple. You have the same optical fiber, you have CO2 laser, but you just need to decrease the power of this laser and make permanent heating. Since refractive index depend on the temperature of surrounding media, and if you introduce local heating, you change the refractive index and you change the effective radius of the fiber, but not permanently. When you turn off the laser, the resonator disappeared. And this profile is presented here in sketch of this experiment. But the problem is when you use heating with CO2 laser, heating, it's 20 milliseconds. So if you have the pulse about 100 picoseconds and heating is milliseconds, and it's completely different orders. But the most important problem is cooling as well. Cooling, it's about 100 milliseconds. So it was a nice concept, but I think it still did not implement it in real life. But it was a nice try, I guess. And one more experiment, maybe just to increase this process or just to make it like people very love to do technology, something on a chip. And it was integration of metallic wire. It was put inside the capillary, and we introduced microresonator with CO2 laser again, and we just introduced the second one, put the metallic wire inside. The metallic wire was etched with an acid, I guess sulfuric acid, and at the place where you have the defect on the surface of metallic wire, it's going to be most ohmic heating in this place. And just using an electric current, you can tune the resonator axial modes of the resonator. like it was before electric current and like it presented here. But of course, the background will be really messy because it's again produced a lot of heat, which is not good enough. One more opportunity to tune it. It's very nice work, actually. One PhD student visited Austin at some point, and he fabricated this fiber loop. When you bend the optical fiber, you will see local changes of refractive index, and these changes are quite enough to introduce optical microresonators with changes about 14 nanometers. And it can be tunable as well, and it provides a parabolic shape profile. But at the same time, it's parabolic just on the top of the resonator. And this part are not parabolic. They will give a huge dispersion. And I think our colleagues from Novosibirsk, they work on this, but I don't know the current progress. Personally, I like to make optical, I like the idea of making optical buffers, which was proposed again when I left the Aston, and it's just an advert of this work. Please see this conference proceeding and also archive article, and maybe they will publish it soon. Instead of different heating effects and mechanical bending, it was proposed to use solitone. Solitone is sending to the microfiber, and it propagates along the fiber here. And at some point, you can launch your pulse into the induced resonator, which was induced with solitone. And it propagates again with slow light, with the idea of slow light. And at some point, you can just read this pulse. Idea was not implemented experimentally, but to start these experiments, we just measured so-called 4-port SNAP Microresonator. We have optical fiber with a SNAP resonator introduced with the CO2 laser. We just measured transmission amplitude of this microresonator, and surface plot is presented here. But at some point, you can just remove this part and measure which power will go through the optical fiber in this axial direction. And the result was quite acceptable, but to my mind, we can do it better, because if you can see, here is the -5 dB maximum losses. But when you measure the same power, the same energy which propagated through the optical fiber, you will see -25 dB. But actually, it's the same profile of the resonator, which was work. One more device, which is really exciting for optical bottom microresonator, really exciting example of applications, is frequency combs. This concept was developed, I think, about 10 years ago, and Misha described how can we use optical microresonator for this. Microresonator should be long enough, and it should be big enough, because to provide equidistant spectra of different, to provide a proper frequency comb, because it shouldn't be as long as you can do it, and it should has a lot of different lines. For this, you need to fabricate microresonators with lots of azimuthal and axial mode, and it's better to have the situation like this when they are cover each other already. And to provide broadband frequency comb, the effective radius change should be really big. This idea was implemented in this technique. The first work, I think, was published in 2000 by Professor Bergs, who just tapered fiber and scanned the tapered region of the fiber, and they found out that changes here is about 2% in effective radius variation, and these 2% are quite good enough for creating a optical microresonator, which can be used for optical frequency comb. It provides very nice free spectral range. It's about 50 picometers, and the same fiber diameter is about 30 micrometers. But the main drawback of most of these techniques, they used something natural, because they use release of mechanical tensions, which were introduced during the drawing of optical fibers. And the maximum you can achieve, maximum of the effective radius variation you can achieve is about 20 or 30 nanometers only. But to produce, to fabricate really nice frequency comb, broadband frequency comb, it was calculated in this work. If you're interested, you can read. It should be hundreds of nanometers. And to realize this idea, we propose to use just HF etching of optical fibers. It's quite simple scheme. Here you have just ordinary optical fibers in a polymer jacket. You can remove polymer jacket using, again, CO2 laser or whatever laser you have. After that, for several seconds, you can dip your fiber into HF acid and remove the cladding, the rest part of the cladding, using hot H2SO4 acid, sulfuric acid. And we demonstrated that, yeah, it works. Maybe the profile should be corrected just to obtain a parabolic profile. But anyway, 290 nanometers effective radius changes were achieved. And actually, this technique is quite good because it provides not sub-angstrom precision, but sub-nanometer precision, and it can be adopted and then it can be integrated, and it's quite easy and straightforward. But the main problem of etching process is a very low quality of the surface, and for this reason, the quality factor of these resonators will be not good enough. But if you just use a CO2 laser polishing, you can make it smooth. And the best achieved quality factor we measured was of 10 to the 6. It corresponds to 1.3 picometer full width at half maximum, which corresponds to the resolution of our device. And one more application, I'll just mention it quickly. It's not application, one more technique for the fabrication of SNAP resonators. It's it's a droplet of water which is introduced inside a capillary fiber. It's actually the same principle, but the light can propagate back and forth here. And I guess it's a very nice step to microfluidics and to sensors. And that is why I mentioned, because I'm going to tell you about the second part of my talk, which I'm working on in Exeter here. Instead of microbottle resonators, here we use just microspheres, which can be fabricated again with the CO2 laser, just melting of standard SMF28 fibers. This microresonators can be put inside a chamber with PDMS, and instead of tapered fiber here, we use a prism coupler, some optics, and the laser. It can be 642 nanometers laser or 780 nanometers laser, and we can detect the different molecules ions, and the main purpose of my current work is the detection of enzymes. Enzymes are presented here. I'm not a biologist. I believe they are very important. It is really nice object to investigation. Whispering gallium modes resonators based on whispering gallium modes or supporting whispering gallium modes, they have really nice quality factor and it provides very nice sensitivity. But when people are talking about sensors based on whispering gallium mode microresonators, it's not actually completely true because they have a drawback as well. A drawback is the high mode volume. Of course, it's relatively high mode volume, but it has orders of micrometers. And to reduce mode volume, it was proposed by my current line manager, Frank Vollmer, to use nanorods of gold or silver just to localize light or just to obtain whispering gallium modes with a very, very small effective mode volume. And here we can attach nanoparticles, gold nanorods, to the surface of whispering gallium mode microresonators. And of course, it spoils quality factor of these resonators almost by order of magnitude. But at the same time, it increases the sensitivity because effective mode volume is going low, is getting smaller. Here is the protocol of my experiments with enzymes. I fabricate microsphere, put it into PDMS chamber, attach nanorods. It's standard nanorods, which were fabricated by nanoparts. They coated with CTAB and diluted. After attaching nanorods, I used to work with several buffers. And this step is just to isolate the surface of microsphere and allow enzymes to be attached at the surface of nanoparticles only. And this step, adding nickel sulfate, is just to attach these particular enzymes because they can interact with nickel sulfate, which was defined by experimentally. As an object of investigation, we use transaminase from Chromobacterium valdesium and Archaeoglobus veneficus. And to tests, we use nanomolar and sometimes picomolar concentrations. And here I'm presenting the changes of frequencies. And it's not frequencies, waveband, of course. And also we can measure attachment events by changing of full width at half maximum, it's delta kappa. And here you can see clear steps. It's an attaching event when you have nanoparticles, nanorods. And after all that procedure I described, we can add enzymes, real enzymes. And here we can also detect them. And the following procedure, we can add different surfactants and cofactors and follow the movements and different conformational changes of enzymes. Hello, yeah, Andrey?
Yes, Nikita. So I didn't get it. Maybe again. What is delta kappa?
Delta kappa, it's full width at half maximum of the resonant line.
I see. So and we see some sharp steps here around 40 seconds or for 45. Is it a touching of the gold particle of the?
Yes.
I see. But we also see some linear growth of the signal as well as in delta lambda and delta kappa. So could you also comment on it, please?
Yeah, it's just a background. It's probably changes of pressure or it's probably changes of temperature because you always have this background. And if you actually start two experiments in the same room, if you have two resonators and two lasers, you will see exactly the same growth. It's just something around.
Oh, yes. So it means that to have a clear experiment, you need another empty system for reference. Yes.
But we usually believe that it is true because steps, they have exactly particular time scale. For example, if someone in the corridor opened the door, it will be maybe 1 second or something like this. But if you have attachment event, it's milliseconds maximum.
I see. So, and at the upper right panel, so this step means a touching of enzyme, yeah?
Yeah. Enzyme, they have a very complicated structure. And when you have nanoparticle, you can see sharp steps. But when you have enzymes, which are actually moving, and you can see a bit different steps. And at the same time, you can see steps here. In the case of nanoparticles, you can see steps on full width and half maximum. That probably means, but you cannot see when you check your delta lambda. And that probably means that refractive index of this medium, which you can try to calculate maybe with Maxwell-Garnett, it did not change. That's why delta lambda is not shifting. But at the same time, you have something for scattering, losses for scattering on the surface of the whispering gallery mode microresonator. And you can see changes of full width at half maximum.
I see. Thank you.
So, and the last slide. It's the hot topic right now because of coronavirus, and everyone, if you have a sensing laboratory, you must do something with virus, or even better to do something with coronavirus. We work almost right now, we work with adenovirus. Adenovirus is an interesting virus because the Oxford team and AstraZeneca team, they used to work with adenovirus to produce their vaccine for coronavirus. They genetically modified something, and it was good working coronavirus vaccine. For the detection of the viral particle, we calibrated our system. This time it was without nanoparticles, gold nanoparticles. It was just whispering gallery mode resonator. I think there is no need to use optoplasmonic sensors. It's just good enough to use optical sensors because nanoparticles and viral particles are quite big and it's easy to detect them. We calibrated our system with polystyrene particles with known radius, starting from 50 nanometers, calibrated our system, and roughly it has these dependencies. And we also changed the concentration of polystyrene particles, starting from 10 femtomolar and increasing by 110 times. And after that, we used the same system to detect adenovirus particles. And here is a very nice result. The main idea of this experiment, when you build a sensor, you need to use 3 different components. First of all, it's the sensor itself. Second, you need to attach some chemistry or biology for selective binding of viral particles. And the third step, it's how can you read the changes of your signal. And the idea of this work is to get rid of the second step. Do not use any biological substances, just calibrating the system and using the value of wavelength shifts should be related to actual sizes of viral particles. Now it more or less works, except this point. We can say that nanoparticles of adenoviruses are about 40 nanometers roughly. But the final point I should mention, it's whispering gallery mode based sensors are quite, they are very nice, but their opportunities for sensing now it seems like going to be finished. And the trend of the last years, or maybe last 5 years, is just to put the active media inside whispering gallery mode microresonators and use them for biosensing. That was reviewed in our Light Science and Application article, which was published a week ago. So please read and ask questions and contact with the group of Fallen. So I'm going to tell thank you to my former laboratory at Aston, to my current laboratory here in Exeter. I'm going to tell thank you to colleagues from Hozhong, from Novosibirsk, from ITMO, of course. If you want to do real photonics, you need to have someone from ITMO and my colleagues from Aston and Exeter, and thank you for attention.
Nikita, thank you very much. So, colleagues, do we have any questions? I see one question from the audience, Vanya.
Thank you very much for the talk, Nikita. My question is about the last slide, about the size of the viral particles. So, as far as I understood, so you basically say that we have a sensitivity for the size of the particles, and then we can, from the detected size, we can claim that there is adenovirus or there is no adenovirus in the data. But is the size enough to define the exact virus, or there are lots of them with the same size? So is this information enough for selective sensing of particular viruses? Thank you.
Yeah, thank you for the question. It's quite a nice question, because the selectivity is the main problem. But if you are going to work with real biological samples like saliva, for example, maybe it is not enough, but maybe in the future you can do it in a better way. But for now, we are aiming to make experiments with a mixture of just 2 different viruses. And I'm pretty sure that it is enough to distinguish different viruses by sizes.
Okay, thank you.
Thank you. And another question from Andrey.
Yes, Nikita, thank you very much for the fascinating talk. So my question about the minimal possible concentration of viruses that you can measure with this technique. So you talk in moles. What was the minimal concentration?
Molars.
Molar.
And nanomolars. Yeah. Personally, I do not like molars at all.
Yeah.
Any other different units. If I try to recalculate it, it should be 10 to the 9 viral particles per microliter. Yeah. I tried to do it, but this is actually 10 picomolars.
Microliter or milliliter?
1 second.
Maybe milliliter.
Oh, yeah, milliliter.
Milliliter. Okay. Okay. Thank you. Mm-hmm.
Okay, and Misha, please.
Hi, hello, Nikita. Thanks a lot for your talk. And I have a question. Maybe I missed something, but how would you prevent unspecific binding of something to your sensor?
Yeah, if you're talking about enzymes,
yes, this one.
We have a protocol, and just quickly one more time, we attach nanoparticles. We covered silica surface with a PAG buffer, and now just to selectively attach enzymes, we use nickel sulfate solution, because we know these 2 enzymes, they must attach to nickel sulfate. It's like a biotin streptavidin reaction, but with the nickel sulfate and this chromobacterium transaminase. But in this experiment, the goal of this experiment, do not use any linkers, do not use any biology, any antibody.
Okay, I see. Thank you.
Okay. It seems that is it. And so I would like to thank again our speaker, Nikita. Thank you very much for a very nice, interesting talk, and fascinating talk, and I hope that you'll join us here at ITMO University. So before we finish, I would like to briefly announce the next seminar. So it will be given next Friday by Dr. Anton Tsipkin, who is the head of the International Laboratory of Femtosecond Optics and Femtosecond Technology of ITMO University, and he will be talking about terahertz aqueous photonics in Russian. So in order to stay updated, please visit our website, please subscribe, including our channel, and thanks again for joining us tonight. Thanks to everyone.
Thank you. Bye.
Все хорошо. Все, спасибо.
Да, спасибо, Никита.